Introduction to multithreading. Multithreading is a core concept in Java that enables concurrent execution of two or more threads. A thread is a lightweight subprocess and multiple threads can exist with a single process. With multithreading, we can perform multiple tasks simultaneously without creating multiple processes, which saves system resources and improves application performance. The need for multi-threading when you want your program to remain responsive and utilize CPU efficiently. For example, in a GUI-based application, you might want to one thread to manage the user interface and another to perform background calculations or network operations. Without threads, such operations would block the UI and make it unresponsive. Java provides built-in support for multithreading through the java.language.thread class and java.language.runnable interface. Those tools abstract away the low-level details and make thread management similar. By using threads, we can divide a large task into smaller ones and execute them in parallel, significantly reducing execution time. In real world applications, multithreading is commonly used in gaming, server side programming, banking systems, and any domain that requires high performance or real time processing. However, it also introduced complexity. Issues like thread interface and memory consistency errors. Understanding the multithreading the groundwork for writing concurrent programs. Java has more frameworks and utilities like the executor framework, thread pools, and concurrent collection have been added to simplify multithreading. Agenda. In this presentation on multithreaded programming in Java, we will follow a structured agenda to help you build your understanding step by step. First, we will begin with a basic introduction to multithreading, where we will explore what multithreading is and why it's essential for modern software development. This sets the stage for deeper technical discussions. Next, we will discuss the thread lifecycle. Understanding the different states a thread can be in, such as new, runnable, waiting, and terminated, for controlling their execution effectively. Then we will explore creating threads. Java offers two main approaches: extending the thread class and implementing the runnable interface. We will examine both along with the best practices for choosing the right one. We also cover thread methods such as start, run, sleep, and wield. Those methods help manage thread behavior. A significant part of the presentation will focus on synchronization, which ensures that threads don't interfere with each other when sharing resources. We will learn about synchronization methods, blocks, and object locking. Then we will study thread communication using wait method, notify method, and notify all method for coordination among threads. We will wrap up with advanced concepts like thread pools, interruption, and callable tasks. Lastly, we will go over best practices, common issues, and debugging tools that will help you write reliable multi-threaded Java applications. By the end of this agenda, you will gain a comprehensive understanding of how to create and manage threads effectively in Java. Introduction to multithreading. Multithreading is a core concept in Java that enables concurrent execution of two or more threads. A thread is a lightweight subprocess and multiple threads can exist with a single process. With multithreading, we can perform multiple tasks simultaneously without creating multiple processes, which saves system resources and improves application performance. The need for multi-threading when you want your program to remain responsive and utilize CPU efficiently. For example, in a GUI-based application, you might want to one thread to manage the user interface and another to perform background calculations or network operations. Without threads, such operations would block the UI and make it unresponsive. Java provides built-in support for multithreading through the java.language.thread class and java.language.runnable interface. Those tools abstract away the low-level details and make thread management similar. By using threads, we can divide a large task into smaller ones and execute them in parallel, significantly reducing execution time. In real world applications, multithreading is commonly used in gaming, server side programming, banking systems, and any domain that requires high performance or real time processing. However, it also introduced complexity. Issues like thread interface and memory consistency errors. Understanding the multithreading the groundwork for writing concurrent programs. Java has more frameworks and utilities like the executor framework, thread pools, and concurrent collection have been added to simplify multithreading. Java thread class. In Java, threads are represented by thread class in the java.language package. This class provides the foundation for multithreading in Java. When you create an object of the thread class, you are creating a new thread for execution within your program. There are two main ways to create a thread using the thread class. The first is by extending the thread class itself and overriding the run method. This method contains the code that should be executed in the new thread. Once the thread object is created, you call the start method. To begin execution, it's important to remember that calling run method directly does not start a new thread. It just executed the method like a normal function call. The thread class provides several useful methods for thread management such as start method, start the thread, run method, defines the task, sleep method, pauses the thread for a specific duration, join method, waits for another thread to finish, getName method and setName method, manage thread names, set priority method, adjust the thread priority. By using the thread class, you gain control over thread behavior. It also includes mechanisms to handle interruptions, detect thread state, and manage thread groups. However, extending the thread class restricts you from extending any other class, which is why the runnable interface is often preferred. Runnable interface. The runnable interface is a functional interface provided by Java for implementing multi-threaded behavior in a more flexible way than extending the thread class. Located in java.language package, it contains a single abstract method run method. When a class implements the runnable interface, it must override the run method to define the task that the thread will execute. The primary advantage of using runnable is that Java supports single inheritance. If you extended the thread class, you cannot extend any other class. Implementing runnable, however, allows your class to remain free to inherit from another class if needed, offering more design flexibility. To create and start a thread using runnable, follow those steps. First one, create a class that implements runnable. Second one, override the run method with the task you want to the thread to perform. Third one, create a thread object and pass the runnable object as an argument to the thread constructor. Fourth one, call the start method on the thread object to begin execution. This method is preferred for applications that separate task definition from thread control. It's also the base for advanced concurrency features like executors. Next, we will explore thread creation using both extending thread and implementing runnable. Creating threads. One of the simplest way to create a thread in Java is by extending the thread class. This method is useful for small tasks where simplicity is more important than scalability or flexibility. To create a thread this way, first one, create a class that extends thread. Second one, override the run method to define the logic that should be executed in the thread. Third one, create an instance of your class. Fourth one, call the start method to begin execution. It's important to note that if you call run method directly, the thread want to run on a separate path. It will behave like a normal method call. Always use start method to trigger true multithreading. While this method is easy to use, it limits flexibility because Java does not support multiple inheritance. That's why in more complex programs, developers prefer implementing runnable. Creating threads. Creating threads by implementing the runnable interface is considered a better practice than extending the thread class, especially in large or object oriented projects. This approach separates the thread execution from the thread logic, making your code more maintainable and flexible. To create a thread using runnable, first one, implement the runnable interface in your class. Second one, override the run method with the task logic. Third one, create a thread object and pass the runnable implementation to its constructor. Fourth one, call the start method on the thread object. This method is preferred when you want to extend another class, you want to decouple the task logic from the thread object, you plan to use advanced multithreading features like executor service or thread pools. We can even use lambda expressions to shorten code when working with Java 8 Plus. Implementing Runnable provides better abstraction and is more suited for modern Java applications. Now that you know how to create threads, let's explore the different lifecycle stages a thread goes through. Thread lifecycle states. Understanding the thread lifecycle is crucial for managing thread behavior in Java. A thread in Java goes through multiple states during its lifetime. The Java thread lifecycle includes the following states. First one, new. A thread is in the new state when it is created using the thread class but has not started yet. It remains in this state until the start method is called. Second one, runnable. After calling start method, the thread moves to the runnable state. Here it's ready to run and waiting for CPU time from the thread scheduler. Third one, running. When the thread scheduler picks the thread from the runnable pool, it moves to the running state where the run method is being executed. Fourth one, blocked. A thread is in a blocked state when it is waiting to acquire a lock to enter a synchronized block or method. Fifth one, waiting. A thread enters this state when it is waiting indefinitely for another thread to perform a specific task. Sixth one, timed waiting. Similar to waiting, but the thread waits for a specific period or join. Seventh one, terminated. Once the thread finishes execution or is terminated, it enters this state. Understanding those states helps in debugging and optimizing multi-threaded applications. Thread methods start and run. In Java, two fundamental methods of a thread are start and run, and understanding the difference between them. First one, start. Start is a method of the thread that begins the execution of a new thread. When you call a start method, it internally calls the run method on a new thread of execution, creating separate call stack for concurrent execution. Second one, run contains the actual code that the thread executes. It's the method where you define the task your thread will perform. However, if you call run method directly, it want to start a new thread, it will simply execute like a regular method in the current thread. Always use start method when you want to true multi-threading behavior. Accidentally calling run method instead is a common mistake for beginners. Thread methods sleep and build. In Java, multi-threading controlling the timing and execution of threads is crucial. Two important methods provided by the thread class to help manage this are sleep and build. Let's start with the sleep method. This method pauses the current thread for a specified number of milliseconds. It is useful when you want to delay execution or simulate real-time intervals such as waiting for a resources or polling for data. During the sleep period, the thread transitions into a timed waiting state and allows other threads to execute. Importantly, sleep method throws an interrupted exception, which must be handled with a try-catch block. Next, let's discuss wield. This method is a hint to the thread scheduler that the current thread is willing to wield its current use of the CPU to allow other threads of equal priority a chance to run. However, it's only a suggestion. There is no guarantee it will actually cause the thread to pause. Wheel method is rarely used in production, but it's useful for testing or specific scheduling requirements. Unlike sleep and wheel does not pause for a specific time, it simply suggests a momentary pause. Both those methods help manage execution flow in multi-threaded programs, especially when coding tasks or balancing performance. Thread priority. Java allows each thread to have a priority, which will influence the order in which threads are scheduled for execution. Priority is an integer ranging from 1 to 10, with 5 being the default value. Thread priorities are used by the thread scheduler to decide which thread should run when multiple threads are in the runnable state. However, thread scheduling is highly platform dependent. Some operating systems may ignore priorities altogether, making it unreliable for strict control. Important notes: priority should not be used as a means of control in critical logic. Thread priority is more of suggestions of the scheduler than a rule. Thread synchronization. In multi-threaded programs, threads often share common resources such as variables, objects, or files. If multiple threads try to access and modify the same resources at the same time, it can lead to data inconsistency, race conditions, or even system crashes. This is where synchronization comes in. Thread synchronization ensures that only the thread can access a shared resources at a time, preventing thread interference and memory consistency errors. Java provides the synchronized keyword to manage access to shared resources. There are two main ways to apply synchronization. First one, synchronized methods. When a method is declared synchronized, a thread activates a lock on the object before executing the thread. Second one, synchronized blocks. A portion of code inside a method can be synchronized by blocking on a specific object, which provides more fine-grained control. While synchronization ensures data consistency, overusing it can lead to performance issues like thread contention or deadlocks. So it's important to synchronize only the necessary parts of code. Synchronized methods. Synchronized methods in Java are used to prevent multiple threads from executing critical sections of code at the same time. When a method is declared with the synchronized keyword, the thread must acquire the intrinsic lock of the object before it can be executed that method. If one thread is already executing a synchronized method on an object, all other threads trying to invoke any other synchronized method on the same object are blocked until the lock is released. Key points: the lock is associated with the object. If the method is static and synchronized, the lock is associated with the class object. Benefits: ensures thread safety, prevents data corruption. However, keep in mind synchronizing entire methods can reduce performance. It's better to use synchronized blocks when you only need part of the method to be synchronized. As applications grow complex, you must balance between safety and efficiency. Overuse of synchronized methods can lead to thread contention and decreased throughput. Synchronized blocks. While synchronized method lock to entire method, synchronized blocks offer more control by locking only a specific section of code. This approach is preferred when only part of the method access shared resources, helping to reduce contention and improve is preferred when only part of the method access shared resources, helping to reduce contention and improve performance. A synchronized block is defined using the synchronized keyword followed by an object reference, which acts as the lock. Only one thread can execute a block synchronized on the same object at a time. Use cases: synchronize access to shared counters or collections, perfect code blocks that update global states. Keep synchronized blocks short to reduce the time a thread holds the lock. Holding a lock for too long can block other threads. Deadlock. Deadlock is a critical issue in multi-threaded programming that occurs when two or more threads are permanently blocked, each waiting for the other to release a lock. As a result, none of the threads can proceed. On the application's freezes. Let's understanding deadlock with a simple scenarios. Thread A hold log 1 and waits for log 2. Thread B holds log 2 and waits for log 1. Both threads are waiting for each other to release the logs, but neither does. This circular waiting results in a deadlock. If two threads call method A on different task objects at the same time, they may enter a deadlock if each acquires a different lock first. How to prevent deadlock? First one, avoid nested locks. Try not to acquire multiple locks at the same time. Second one, lock ordering. Allows acquire locks in a specific consistent order. Third one, timeouts. Use try lock mechanism with the timeouts to avoid indefinite waiting. Fourth one, deadlock detection tools. Tools like Visual VM or JConsole can help detect deadlocks threads is running applications. Deadlock are hard to detect and debug, especially in large applications. The key is to design your code with the safe logging strategies. Thread communication. Wait, notify, notify all. In Java multithreading, sometimes threads needed to communicate and coordinate their actions, especially when working on shared data. Java provides inter-thread communication mechanism through three essential methods defined in the object class: wait, notify, and notify all. Those methods are used with the synchronization blocks or methods to allow threads to cooperate rather than the compete for resources. First one, wait, causes the current thread to wait until another thread invokes notify or notify all on the same object. It releases the acquired lock and puts the thread in a waiting state. Second one, notify, wakes up a single thread waiting on the object monitor. If multiple threads are waiting, one is selected. Third one, notify all, wakes up all the threads waiting on the object's monitor. Important rules. Those methods must be called inside a synchronized context. Failing to do so throws illegal monitor state exception. Using wait and notify allows efficient communication between threads, reducing CPU usage by avoiding polling. Volatile keyword. In Java multithreading, memory consistency is just as important as synchronization. One tool that helps ensure this is the volatile keyword. It is used to indicate that a variable's value may be changed by multiple threads, and that changes made by one thread should be immediately visible to others. Without volatile keyword, the JVM and CPU may variables for performance reasons, which can lead to threads reading inconsistency values. When a variable is declared as volatile, guarantees. First one, visibility. Changes made by one thread are immediately visible to other threads. However, volatile does not provide atomicity. For compound actions like count plus plus, use synchronization, or atomic classes like atomic integer, use volatile. For flags and state indicators, when atomicity is not required, when you want to lightweight visibility guarantees. Thread pools. Creating a new thread for every task in a program can be resources intensive, especially in applications that need to perform hundreds or thousands of concurrent operations. To address this, Java provides thread pools, which manage a collection of worker threads that can be reused, reducing the overhead of thread creation and destruction. A thread pool maintains a pool of pre-instantiated threads. When a task arrives, a thread from the pool is assigned to execute it. Java provides thread pools through the executor service interface and executor utility case. Types of thread pools. First one, fixed thread pool, a fixed number of threads. Second one, cached thread pool, creates new threads as needed, reuses old ones. Third one, single thread executor, a single thread to process tasks sequentially. Fourth one, scheduled thread pool, for executing tasks at scheduled times or intervals. Thread pools are essentially for building scalable, responsive, and efficient Java applications. Callable and future. Unlike the runnable interface, which does not return a result or throw a checked exception, Java provides the callable interface for tasks that return a value and may throw an exception. It works together with the future interface to retrieve the result once the task is complete. This is especially useful when you want to execute background task and get its output at a later time. First one, callable interface, defined in java.util.concurrent, has a single method we call method throws exception, return a result of type v. Second one, future interface, represents the result of an asynchronous commutation. Advantages: supports concurrent programming with written values, allows you to cancel tasks, can block or poll to retrieve results. Exception handling: call method can throw checked exception. Get method may throw execution exception or interrupted exception. Using callable and future is a step toward asynchronous and non-blocking Java applications. Domain threads. In Java, threads are classified into two types: user threads and domain threads. While user threads are essentially for program execution, domain threads are background threads that support user threads but are not crucial for programming termination. A daemon thread runs in the background to perform tasks such as a garbage collection, monitoring, or housekeeping. The key point is the JVM exists automatically once all user threads finish. Use cases: background logging, autosave futures, cleanup utilities. Difference from user threads: user threads prevent JVM shutdown, domain threads do not. Interruption: in Java, threads may need to be stopped or notified to stop during execution. However, Java does not provide a direct method to forcibly kill a thread. Instead, it offers a safer mechanism known as thread interruption. Thread interruption allows one thread to signal another that it should be stop what is doing. This is achieved using the interrupt method. Key concepts: first one, interrupt method sends an interruption signal to the thread. Second one is interrupted method checks if the thread has been interrupted. Third one, interrupted exception thrown when a thread is blocked and is interrupted. When a thread is sleeping or waiting, calling interrupt causes it to throw an interrupted exception. You should handle this exception and cleanly stop the task. Interruption is a cooperative mechanism. Threads must check and respond to the interruption request. To truly understand multithreading, it's important to difference between a process and a thread. A process is an independent program in execution with its own memory space, system resources, and at least one thread, by default the main thread. It's managed by the operating system and is isolated from other processes. If you launch two instances of a word processor, each one is a separate process with its own memory and data. A thread, on the other hand, is a lightweight subprocess. Multiple threads can run inside a single process and share the same memory space. This shared memory allows threads to communicate more efficiently than process, but also introduce synchronization issues. Imagine a restaurant. The process is the entire restaurant operation, while threads are individual waiters handling customers. They all work in parallel but share the kitchen and order system. If two waiters try to grab the same dish, just like threads accessing shared variables without synchronization, Java applications are multiple threaded by default. The main thread runs first and from there other threads can be spanned. Wait. Threads in a process are not isolated from one another, meaning changes made by one thread are visible to others, which is powerful but risky without proper synchronization. Understanding these differences helps clarify why threads are more efficient but need carefully control. Unlike processes, threads are cheaper to create and manage, making them ideal for a task that require high concurrency. Now let's look at how Java represents threads in code. Best practices: writing efficient multi-threaded programs in Java requires more than just knowing the syntax. Poorly managed threads can lead to performance bottlenecks, bugs, or system crashes. Here some key best practices to follow. First one, minimize the shared data. Second one, use a thread safe collections. Third one, prefer executors or manual thread management. Fourth one, use automatic variable. Sixth one, detect deadlocks early. Seventh one, handle interruptions gracefully. Eighth one, test thoroughly. Ninth one, monitor with the tools. By applying those practices, you will write more maintainable and high performance multi-threaded Java applications. Common issues: the power and flexibility that multi-threading offers, it introduces several challenges and pitfalls. Here are the most common issues encountered in Java multithreading and how to address them. First one, race condition. Second one, deadlocks. Third one, starvation. Fourth one, live logs. Fifth one, memory consistency errors. Sixth one, improper use of a sleep or wait. Seventh one, thread leakage. Understanding issues is for building reliable applications. In your final slide, we will look at the tools for debugging multi-threaded Java programming. Tools for debugging threads. Debugging multi-threaded applications is significantly more complex than single-threaded ones. However, Java provides powerful tools and utilities to help monitor, analyze, and debug thread behavior. First one, thread dump, a snapshot of all running threads and their states. Second one, JStack, a command line tool that shows thread stack traces of a run Java process. Third one, Visual VM, a graphical tool and monitors JVM performance, memory usage, and thread activity. Fourth one, JConsole, a Java monitoring and management console. Debugging is an essential part of developing multi-threaded applications. Using those tools will help you detect issues earlier, analyze performance, and ensures that your application runs smoothly. Conclusion. As we conclude this presentation on multi-threaded programming in Java, let's revisit the key takeaways that highlights the importance and power of using threads effectively in Java applications. To build efficient, scalable, and multi-threaded applications, developers must use synchronization and thread communication mechanism wisely, avoid unnecessary complexity, and always follow best practices. Thank you for participating in this session. With the knowledge you have gained,